Okay, so here's a video on basically how to work out, this is a C-type problem, okay, it's a mass-to-mass conversion, and this is hopefully going to help you with the lab analysis for decomposition of sodium carbonate. So, I split this up so that we have mass, molecular weight, and the number of moles on one side of the column, and then you can see the balanced chemical equation at the top here. So we're going to start out by filling out the information that we know. And so we were told that we're actually going to be heating or decomposing 2 grams of sodium bicarbonate. Okay, and we're trying to find out how many grams of this sodium oxide compound, this solid sodium oxide compound, is going to be left in the crucible. Okay, and depending on what the answer to that is, that will then hopefully allow us to figure out whether or not sodium oxide is actually the product that's formed or if it's something else. So at the moment, it looks as though this is all the information that we have. But obviously, if we have a periodic table to hand and we have a calculator, we can also work out the molecular weight or the molar mass of sodium bicarb, which is 84 grams per mole. Okay. Well, we should also now be very, very familiar with this equation of the number of moles is equal to mass divided by molecular weight, in which case we are able to work out the number of moles that we actually start off with, okay, of sodium bicarbonate. So essentially we would do number of moles is equal to the mass, which is 2 grams, divided by the molecular weight, which is 84 grams per mole, and we're going to get an answer here of 0.0119 moles. I'm using 3 significant figures here, all right? That's why I've left it as 0.0119. 3 figures as a general rule is usually a good standard to adopt when doing these types of calculations. Okay, now the question is, why is that helpful? Well, this is helpful because what I'm now able to do is to convert this number of moles into the number of moles of sodium oxide. Okay, so this has now essentially become a straight mole-to-mole conversion. And if we remember, I'm just going to remove this for the time being, not to confuse things. To work out the moles of sodium oxide, we're going to take our moles of sodium bicarbonate. Okay, this is from here. And we're going to times it by our conversion factor. Now, in this case, our conversion factor is going to be 1 divided by 2, because the coefficient for sodium oxide is 1, the coefficient for sodium bicarb is 2, and so when we actually go through this process and we perform this calculation, we're going to get a final answer of 0.00595. Okay, so again, why is that helpful? Well, we may not know the mass of sodium oxide yet, but if we know the moles and we know the molecular weight, which we can work out from a periodic table, we'll then be able to find out the mass. So if you work out the molecular weight of sodium oxide, 2 sodium atoms, 1 single oxygen atom, comes out to be 62 grams per mole. And so we just simply need to rearrange our moles is equal to mass divided by molecular weight equation to give us the mass is equal to moles times the molecular weight. So essentially, our mass is going to be equal to 0.00595 times our molecular weight of 62 grams per mole, and we get a final answer of 0.369 grams. So 0.369 grams. So essentially, if we start off with 2 grams of sodium bicarbonate and we decompose it, right, we heat it till it decomposes, if sodium oxide is actually the product, we should expect around 0.369 grams. I'm saying around because obviously there may be some product that's lost, it may not be completely decomposed, there's all different things factors that come into play, but it should be approximately about 0.369 grams. The values that you are given in order to work out the rest of the equations are going to be very similar. So you can use this approach here as your starting point to then be able to work through problems 1, 2, 3, and 4.